Okay, everyone, let's get started. So first of all, we released the homework 3 today, and we expect the due is at the end of this month. So a little bit shorter time, like for 10 days or 11 days, but the number of problems is relatively small as well. Like 8 problems, all written problems. It's just to check your understanding of the graphing models and ask you to do some kind of like manually write down the steps of performing some product algorithm. We have went through some example in the class. So homework problem is no more complex than the class example. So please start looking at homework 3 right now. So although the number of problems is smaller, but please do not like try to hurry up at the and at deadline. Okay, so let us continue with variational inference, which we made a initial discussion at the end of last lecture. So we want to use this Gaussian mixture model, like GMM, as an example to motivate variational inference, right? So what is Gaussian mixture model? It's a probabilistic version of the k-means clustering. So k-means clustering is the most commonly used approach to discover cluster structures from data. In some scenario, they call it unsupervised learning. But basically, you can view like, okay, you're given a set of feature vectors, right? How do you group them naturally to form some clusters? How do we represent? How do we use a probabilistic modeling framework to represent this cluster structure, right? This is how Gaussian mixture model does, right? So suppose we got n data points, x1 to x big N, and we preset the cluster number k. So you can set k equals to 5, k equals to 10, and so on, right? And then we use the following sampling procedure to model the cluster, right? So we're going to sample each data point n. Like, how do we sample each data point n? We first sample a cluster membership Zn. Zn is a one-hot encoder, like, represents which cluster this data point n belongs to. For example, here's one hot encoder. That means there's only one element is 1, corresponding to the cluster index, which is just third cluster, right? So remember, one hot encoding means that a vector of all zeros except only one element being 1. And then we can write down the prior of the cluster membership, P of Zn, as the categorical distribution. Of course, this categorical distribution is parameterized by this probability vector. So this we have discussed the categorical distribution before, right? It is parameterized by a probability vector pi. This pi1, pi2 to pi big K represents the probability that any data point belongs to the corresponding cluster. Right? Their summation must be 1. And then given the cluster membership, like we sampled for nth data point, then we sample the feature vector xn from the corresponding Gaussian distribution. Right? So here, the basic assumption is that we assume that each cluster is generated by a particular Gaussian distribution. Right? It has its mean, which you can view it as a cluster center. It has a covariance matrix. You can view it as shape of this cluster. Right? Then, given the sample cluster shape for data point n, then you can pick up the corresponding cluster mean and covariance to generate or sample the feature vector xn. Right? So here, for convenience, we can write down this likelihood in this form, right? Product of the Gaussian likelihood to the power of the indicator z and k, right? Remember, there's only one element among those z and k's being 1, right? All the other elements are 0, so that means the power to the 0 is simply 1. So any questions so far? We're just trying to refresh our mind. Okay. So now, given this model, our task amounts to inferring all those parameters which decides the cluster parameters, like what is the prior probability factor pi, which decides how likely each data point belongs to every cluster, and cluster specific mean, like you have big K clusters, you have big K cluster means, cluster specific covariance matrices, right? And also we want to know that given these n data points, what's the posterior distribution of every cluster membership? That's our goal, right? So you can see that our goal is twofold, right? One is that, okay, we want to estimate posterior distribution of those cluster memberships, right? The other, the other fold is we want to estimate those parameters which decides this model, right? Cluster specific mean, cluster specific covariance. You can view that these parameters actually determines where the location of those clusters are, right? What is the large of the span of clusters? So to address this learning problem, right, one simple idea, right, or straightforward idea would be, okay, because this model, right, this is joint distribution involving both the cluster membership, they are categorical variables, right, and also the continuous random continuous observation X, right? So if you write down the marginal, if you write down the joint probability, it is a product over every data point, where you're going to first sample the cluster membership, right? P of Zn given pi vector, and then the likelihood of the observation Xn given the cluster membership Zn, right? So one might consider that why not we first marginalize out those cluster membership. Right? So this is fairly easy. So because if you look at for a particular data point, say Xn Zn, right? The joint probability is P of Cn given pi, and also we got this product, right? Xn mu k sigma k to the power of Z and k, right? So if you want to marginalize our Zn, what should you do? Any thought? Any guess? What? Yeah, integrate. But here Zn is discrete, right? So integrate becomes a summation, right? You just sum over all possible values of Zn, right? We know that Zn, well, Zn is a one-hot encoder, right? So that means, but it only can take k possible values, right? Is 1, 0, 0, 0, 0, 1, 0, 0, until 0, 0, 0, 1, right? So for every possible choice, like k, Zn, the first one-hot encoding corresponding to that Zn, the action belongs to the cluster 1, right? So this guy will be pi k, right? The probability that the data point Xn belongs to cluster 1 will be pi k, and then the corresponding likelihood will be mu k sigma k, right? Of course, you have to enumerate all possible cases from k equals to 1 to plus k equals to bk, right? It's fairly straightforward. Then you get marginal probability or marginal distribution of a single data point Xn, right? Because all those data points are independent, so their joint likelihood will be just a product over the marginal likelihood of every data point, right? So something like that. So in this way, you have only the distribution over the data points X, right? Does it make sense? Right? And then you can maximize the marginal distribution. Sorry, I need to remove I need to wipe out what I wrote, right? It's kind of overlap, right? So you can see that product on the outside becomes summation and the logarithm of each marginal likelihood of the data point, right? Which is just the summation mixture of the Gaussian. Does it make sense? Right. And then we just need to maximize this likelihood, marginal likelihood. We need to put some constraints because all those pi k's are probabilities, right? The summation must be 1, so we got this additional constraint, and we just do the optimization. So this seems a fairly straightforward approach of doing this, right? And seems we can avoid the trouble of estimating the marginal, estimating the cluster membership, which is discrete. And also, once we have get those parameters pi k and mu k and sigma k, it's very easy to compute the posterior distribution of the cluster membership of Zn given X, right? Because it starts from like U X and Zn and divided by Xn, right? So this guy is just a mixture of this guy, right? And this guy just to pick up whatever Zn's value, like say it's a case cluster, right? Multiply with pi k with this cluster specific likelihood, right? So this is one solution, right? It looks like simple and straightforward and avoid some trouble, but there's a optimization issue with this. Right? So you find that this method severely suffers from the so-called singularity issue. Right? So what does it mean for singularity issue? So basically, when we maximize this marginal likelihood over, let me erase all my previous writing, right? So if you maximize this guy, right, you need to initialize those pi k's, right? And also those mu k's and sigma k's, right? If you happen to initialize some cluster center to be close to one data point, then the optimization is very easy to collapse onto that data point. What does it mean? Okay. Let's use a diagonal covariance as an example, right, for simplicity. So basically, we assume that, okay, this sigma k is just the diagonal matrix, right? And then we found that if you initialize your cluster center is close to some data point, right, then the optimization, like the maximization of the marginal likelihood, tends to collapse this cluster onto this single data point, meaning that the mu k might converge to data point. Let us denote this data point by Xn, and the covariance here is diagonal, right? For the one-dimensional case, it's just a scalar. It tend to be very, very small, like to be close to 0. Right. Are we on the same page? Right. I'm describing any question regarding the issue I just described. Everyone's good about that, right? And next we'll talk about why we have this singularity issue. So first, we do not want our cluster to be centered on one data point and with variance to be very small. We do not want that. If we have that, that means our clustering procedure fails. Right? We want to find a group of data points that are close to each other, right? They're more similar to each other than to others, right? But now you just collapse your cluster onto one single data point. So what's the point? What's the meaning of doing clustering? Right? Of course, this is not something we want, right? But what problem that might cause this collapse? Right? The problem comes from the property of the Gaussian distribution. So if you look at the Gaussian distribution, let's just use one dimensional point as the example, right? It's just one dimensional Gaussian distribution. So this is some arbitrary Gaussian distribution with mean and variance, right? So now I want to ask, at which place this density is maximum? Yeah, at mu, right? So if you take your input to the Gaussian density function, x to be at the right at the mean mu, your density is the largest for sure, right? And secondly, right, if you're allowed to change the variance of the Gaussian, like suppose I got x, right? I got x here and mu here, and x and mu is the same, right? So now suppose you have the flexibility to further vary the variance sigma. How do you make your density at mu to further increase? Yes, lower the variance, right? So if you reduce the variance, right? If you reduce variance, what will happen is that your Gaussian mass is more and more concentrated toward the center, right? Where the mean is, right? So if you keep doing this, right, you see that you get taller and more spiky Gaussian density, right? And if we take an extreme case, like we take the variance or standard deviation to close to 0, right? So then your Gaussian density is kind of like toward a delta function. So delta function means you have an infinite tall spike, right? When your variance is going to 0, right? This can be seen by taking the, if you look at the variance, if you look at the density, if you look at the density of the Gaussian distribution, if we specifically intentionally set x to be mu and take sigma goes to 0, you see that the result will be infinite. This is the property of Gaussian distribution, right? So now let us keep this in mind and look at our learning procedure. So suppose we initialize some mu g and sigma g. This corresponds to a particular cluster, right? It has its mean and variance, right? Suppose my initialization is very close to some data point xn, right? And variance, it might be not that large, not that small. It might be flat. Let me use another flat at the beginning, right? So this is my mu g. So this is a data point xn, right? So, and remember, our goal is to maximize the likelihood, right? So to maximize the likelihood, if you take a look here, right, you want to make the data point when evaluated as some cluster-specific Gaussian to be as large as possible, right? So here xn is fixed, but the cluster mean and variance is varying, right? You need to optimize mean and variance. So to increase this likelihood of xn, say, evaluated on a Gaussian parameterized by mu g and sigma g, how should we tune mu g and sigma g? How should we adjust mu g and sigma g? And thought? we got data point xn here. Right? So this is my data point xn, right? So this is my initialization of mu j, and sigma j is my initial Gaussian, right? So now I want to move this Gaussian such that when xn evaluated its likelihood with this Gaussian, the likelihood is as large as possible. Then how should we adjust mu j and sigma j? David. Yes, exactly right. So I want this likelihood to be as large as possible, right? Xn is fixed, but now I have freedom to vary the position of the Gaussian and also the span of the Gaussian. Then what should I do, right? What I do is just I'm gonna move my mu j to overlap with xn, right? And then at the same time, I try to squeeze my variance to be as small as possible. Okay? So of course, in the extreme case, if you can make your sigma j to be 0, then your likelihood becomes infinity. But of course, like due to some numerical problems, also some balance of other likelihood evaluation on xn, right? On other cluster specific Gaussian, sigma j not really goes to will not really go to infinity, right? But sigma j will be tuned very, very small. And as a result, you got a mu j to be collapsed on some data point, your variance to be very, very small. That means the corresponding cluster collapse onto that data point. That's the major issue of our strategy, that we simply marginalize out the cluster membership distribution and simply maximizing the marginal likelihood. Right? The issue is that if you happen to initialize your cluster mean to be close to any data point, it's very easy to drive the optimization to collapse your cluster specific Gaussian on that specific data point. That's a very bad local optimum, which we do not want at all. Any questions so far? Okay, then how do we address this problem, right? So we know that the problem arises from marginalizing out the cluster membership variables. So we think of like, why not we preserve the posterior distribution of cluster memberships, right? Why not we jointly estimate the model parameters, cluster mean, cluster covariance, prior probability vector, and also the posterior mean of the cluster memberships for every data points. Right? We expect that in doing so, we can avoid that singularity issue. So the answer is we can jointly do that. Right? And the joint estimation procedure is usually carried out by the so-called EM algorithm. It's called, the full name is expectation maximization algorithm. So before we look into the details of EM algorithm for Gaussian mixture model, right, we want to look at a general case. We want to look at a general framework where we can apply the EM algorithm, and you see that Gaussian mixture model is just an instance of EM algorithm application. Right? So in general, suppose we got a model, right? This model is governed by some parameter theta, right? The theta is just the points, it's just hyperparameters. We do not assume they're random variables. Or in other words, we're not interested in estimating any posterior distribution regarding theta. We just want a point estimation. And then we assume that there is a latent random variable z sampled from some prior distribution controlled by theta. Then given a latent random variable z, we sample the observation x. So we're interested in estimating point get point estimation of this parameter theta, and also get posterior distribution estimate of this latent random variable z given x. That's our goal. So in Gaussian mixture model, theta corresponds to this pi vector, right? The prior probability vectors. And the cluster specific mean and covariance. Right? And the z in the Gaussian mixture model corresponds to that cluster memberships. Right? Any questions so far? So if you look at the marginal distribution of the data, right? So here X is the observation, is the data. In the Gaussian mixture model, it's just the data points, right? You can view it as a set of feature vectors. Right? If you want to look at the marginal distribution of the data given, the model parameters data, right? You need to marginalize out the latent random variable z according to its joint distribution. Right? The joint distribution is p of x and z given theta, and you marginalize out z, you just integrate out. So in the Gaussian mixture model, right, we know that this guy has an analytical form. It does have a closed form. And if we want to directly maximize this guy with respect to theta, there is some optimization challenge with the singularity issue, right? So now let us come out another way of doing this, another way of maximizing this guy. So, and if you use that way, right, which we call EM algorithm, you can avoid the singularity issue. So how to do that? Right? The idea is to construct a lower bound of the log marginal probability of the data. Right? So this guy we discussed before, the log marginal probability of data is also referred to as the model evidence. Right? So if we look at the model evidence, log model evidence, right, we know that the marginal distribution of the data is the marginalization of the joint distribution with respect to the latent variable z. Right? So this is log. Inside log, there's an integration. So now we introduce a third distribution, Q of z. So here Q of z is just a distribution, right? Any valid distribution, and Q of z is non-zero during all possible values that can take z. Right? This is the basic assumption. Right? And then we can write this joint distribution equivalent by dividing the joint distribution by QZ and multiplying with QZ. Does it make sense? It's the same because we can cancel QZ out, right, in the denominator and numerator, right? But why do we introduce this additional distribution Q of Z? Because we can leverage the Jensen's inequality. So remember, Jensen's inequality tells us if a function is a convex function, right? And then the expectation of this guy, that's not equal to the expectation of the function element, right? And here, log is a concave function. In other words, negative log is a convex function. Right? So then you can apply that to immediately get this result, meaning that you can switch the integration and the logarithm, then you get a lower bound. So this guy is where we should put inside the integration. Does it make sense? This is just says logarithm of expectation of expectation on the Q of Z with bigger than or equal to expectation of logarithm over this fraction. This makes sense, right? Just one step of applying Jensen's inequality. Any questions so far? Okay, and then we'd like to check, right? What's the difference between your true model evidence and your lower bound, or evidence lower bound, right? So it's fairly easy to derive that your true model evidence is equal to the lower bound, which is you derive from the Jensen inequality, plus the KR divergence between your introduced third distribution Q of Z and the posterior distribution of Z given X and given model prime theta. How do we see this, right? How do we see this? You can just write down the definition, right? This is a two integral. If you merge this log term and this log term, right? Summation of two log terms is log of the product. Like you see that Q of Z canceled, and P of X Z given theta divided by P of Z given X is exactly P of X given theta. And the integration actually is constant to P of X given theta, so you can move P of X given theta outside, you get this. Again, you are not required to follow every step we discussed in the class. Right? Again, we highly recommend you after class you derive it by yourself, right? Follow the slides. It's relatively straightforward, right? So by applying the Jensen's equality, we can see that we can decompose the true model evidence into the summation of two terms, right? One is the lower bound, the other is the KR divergence. So from the lower bound, we see that actually the lower bound is determined by two inputs. One is model prime theta. The other is actually the distribution introduced, Q of Z. And the Q of Z can be arbitrary non-zero probability densities, right? And then the gap is the KR divergence between your introduced to distribution and the true posterior distribution of Z in X and theta. Right? So this brings in an opportunity. We kind of augment. If you look into the lower bound, right? We kind of augment the function you want to optimize by introducing an additional free distribution Q of Z. And then we want to leverage this lower bound to optimize the model evidence, the true model evidence. How can we do that? So first, when does the lower bound meets the true model evidence? Any observation? David? Yes, exactly. Right? When Q of Z equals to the posterior distribution Z given X and given current theta, you know that the KR divergence now is 0, right? And then your lower bound is exactly the same of the marginal distribution given the current theta. So actually, for any theta, right, arbitrary theta, right, if you can properly compute the current posterior given X and given current theta, you shove it into the lower bound, you find out you exactly recover the model evidence, right? So we're going to leverage this fact to gradually increase the log model evidence but without directly maximizing this. How can we do that? Suppose we start from some theta, right? The theta can be arbitrary initialization you like, right? For example, you can take it to be 0.2, right? 0.3, whatever. Right here, I just use a scalar as an example, right? That applies to vector case, right? So we know that when you take Q star, QZ to be the posterior of the Z given X and given the current setting of theta, your lower bound has already been equal to the true model evidence where your theta takes your initial value of say 0.2, right? Does it make sense? Right? As I said, right? We can pick up any initialization of theta like 0.2. And now I set my Q star Z, my QZ to be the posterior distribution of Z given X and given current theta value. Then I can guarantee my lower bound currently to be the same as the true model evidence when theta takes 0.2. Does it make sense? So now we fix Q star Z, right? So Q star Z, remember, it is taken as the current posterior of Z given X and given theta. Theta, see, we have taken the current value to be 0.2, right? Now I set my theta in my lower bound to be free. So it is only a function of theta right now. I'm gonna maximizing this lower bound function, right? Only with respect to theta. Does it make sense? Right? I maximize this function, right? Of course, when I find out some new theta, say equals to 0.3, I got my lower bound value. You got theta new equals to 0.3 with the same distribution Q of Z, right? Will be no less than the previous value where you see that only takes 0.2. Does it make sense? I just maximize this function with respect to theta. And then the next observation is that, okay, we know this guy must be a lower bound of the true model evidence where the theta takes the current theta value, which is 0.3. Right? And only if we want our lower bound to be the same of the model evidence at new theta value, you have to update your QZ, right? To be the posterior distribution on the new theta. But from this, just one step, right? We find out we have already found a new theta which increase the marginal, the true model evidence as compared with the previous theta value, right? So previously we take theta equals to 0.2, and through computing the posterior distribution of Z given theta equals to 0.2 given X, we plug in into the lower bound, then we fix it, and we optimize the lower bound with respect to theta only. We get theta new, then we can ensure that on the theta new, say 0.3, the log model evidence is bigger than the model evidence on the previous theta value. Any questions so far? That's the idea. So you can see that throughout this procedure, we never really compute the log marginal probability, right? The model evidence. We never really compute the model evidence, right? We just use the lower bound. We just optimize the lower bound. Right? But we can guarantee that your update of lower bound will improve or increase the log, the model evidence. So lower bound is like a bridge. It's like bridge to push your optimization toward increase of the mild evidence. So now let us look at the general framework of the EML algorithm. Right? So first, we're going to choose an initial setting of the theta, right? We denoted by theta nu, right? And then we just repeat the following two steps. In each iteration, right? We're gonna take the current theta value, we denote by theta old. Then we first compute under the current theta value, which we denote by theta old, what is the posterior distribution of the latent random variable z. They will plug in this Q of z into the lower bound, mild evidence lower bound. Okay? We fix Q of z. Then only maximize the lower bound with respect to theta. Then we get a new value of theta, which we denote by theta nu. And the theta nu guarantees to increase the log mild evidence. So you can see that two steps, right? First step, given the current theta value, theta old, we compute the posterior distribution. This is called E step, expectation step. And the second step, we plug in the current posterior under theta old, right, into my lower bound. And then maximizing the lower bound with respect to theta, this is called M step. Then we get my update of theta. And this guarantees to increase the mild evidence. And every step, every iteration, you run this two step, increase to improve the mild evidence. You just keep doing that until your improvement is too small and we need to stop, or some maximum number of iterations are done. This is called EML algorithm. David. Oh, can I see it again? We only care about point estimation of theta. Yes, you're right. We kind of like consider two parts, right? To optimize. One is the theta, which are model parameters. We only care about their point estimation. The other is the posterior distribution of the latent random variables. We assume that we are able to compute that given theta. Of course, if you're asking if I can compute the posterior of theta, no, the EML algorithm cannot do that. Any other question? So if we can visualize the whole optimization procedure, our goal is to maximize the log marginal probability. We start from say theta old, right? This is where the log marginal model evidence given theta old, right? So the optimization procedure is two-step, EMM, right? The E step is to compute the posterior distribution of z given x and the given current theta, right? Then you plug in this current posterior into my evidence lower bound. And next, I run M step, right? I run M step to maximize this lower bound with respect to theta only, so I get a new theta. Okay. And with this theta nu, because it's a lower bound, the true model evidence on the theta nu must be at least above this lower bound, right? So you can see that your theta nu indeed increases the model evidence. So this is how EML algorithm works. Right? If you feel a little bit uncomfortable on that, it's okay. It's totally fun, right? So you can just look into that and say and consider and just think of like how these two steps works and to keep increasing the model evidence. Any questions so far? Okay, Then let us look at how do we instantiate EM algorithm in the Gaussian mixture model, right? This is our Gaussian mixture model, right? Just quick review. The modeling where for every data point, if you want to sample that data point, we're going to first sample the cluster membership Zn, which is a k by one hot vector. And then we got prior over this Zn, which is categorical distribution. And then given Zn, we sample Xn according to the cluster specific Gaussian, right? So this is the joint distribution, right? So theta includes the prior probability vector, the cluster specific mean, and cluster specific covariance matrices, right? And the data includes the random variables includes the cluster membership variable Z and also the observation X, right? So because those data points are assumed to be ID, so we're going to write down it's a product from data point 1 to data point n. Then inside each product is the joint probability of Xn, Zn, data, right? So if you want to conduct, sorry, if you want to conduct the EM algorithm, in the E step, we need to compute the posterior distribution of the cluster membership given data points X and given the current data, right? And it turns out to be fairly easy to compute that. Right? If we discussed before, right? When we introduced Gaussian mixture model and given the model parameters, how do we estimate, how to compute the posterior distribution of cluster membership for every data point, right? So it is just here, right? So here gamma nk means the posterior probability that the nth data point belongs to a cluster K, which is just pi k. Pi k old means that given the current parameter, which is theta old, right? Pi k old is probability, prior probability that the data point belongs to a case cluster. Then multiplying with the likelihood of Xn if it is generated by case cluster, right? Case cluster specific Gaussian, right? And you need to normalize it because this guy is a probability. Right? You normalize it by summing over all possible cluster choices. And then once we have got my E step, that is the posterior probability of the cluster membership for every data point, right? We can use it. You can see that this is categorical distribution, right? So it just goes through every data points. For every data points, it's categorical, and the parameters are just gamma in case. Right? And in the M step, we're gonna maximize the lower bound, right? So this is the lower bound is expectation over QZ and logarithm of the joint distribution over Q of Z, right? This is where we get from how we get from the Jensen's inequality, right? If we just go back to see our derivation is here, right? It's here. But here Q of Z, right? Q of Z is a discrete or categorical distribution, right? So the integration now becomes a summation. And we got parameters of Q of Z, right? These are gamma and case, right? So that's where we derive, that's how we derive the model evidence, right? It's you have to enumerate all possible values that those memberships can take, right? And the sum over the probability of QZ times the log fractional between the joint distribution, joint probability density, and Q of Z itself. But here, because our model parameters theta are all in the joint probability, it is not in Q of Z, right? So Q of Z can be seen constant, so you can view it as a summation over Z, Q of Z, and the log joint probability. And the other log QZ, you can just throw out, right? So, and then according to the form of the joint distribution, if you take a logarithm, it's just the sum over data points, sum over possible clusters, and the indicators, right? ZNK log pi k and ZNK log the likelihood here, right? And if you take expectation, essentially you're going to take expectation over each indicator, right? Each cluster membership indicator, right? It's very simple. Just it is just the gamma indicator. Right? And eventually you get your objective function in M step. Then to update pi k, mu k, and sigma k's, we just need to take the gradient. Take the gradient, we set gradient to be 0, and it's good to see that solving the gradient being 0 is analytical tractable. You see that the new pi k is kind of like reorganize those gamma and k's. Right? So just look over the probabilities of every data points, their posterior probability being cluster k, normalize it. Okay. And the mu k and the sigma k is even more interesting. Okay. So you can see that mu k is a weighted average of all the data points, where the weight is each data point xn, the posterior probability, it is belong to cluster k. And similar observation applies to sigma k. And then we have derived the updating rule, right? We just keep doing this YAM steps, right? And we initialize some kind of like pi vector, theta vector, right? And then we perform E step, right? And then we perform M step to get the updates of pi k, mu k, and the sigma k to finish one iteration. And then we use this pi k, mu k, and sigma k to compute gamma and k's again in E step and doing M step. Right? Keep doing this, keep doing something convergence, then you have done for your EM algorithm. Any questions so far? It's fairly straightforward, right? And I want to point out that by doing this, we can effectively prevent the singularity issue. Why? David. Yeah, of course, it is the consequence of maximizing all the evidence. But if you want to do a little bit more analysis, you just look at the updating, right? So you can see the updating, right? The updating of every mu k and sigma k, they involve all the data points, right? Unless you intentionally set, say, gamma and k to be biased, like to be very, very biased, like only one element is 1. Remember, this is a probability vector, right? And all the other elements 0. Well, you can see in some sense, in this extreme case, your mu k might collapse onto some data point, right? But the truth is that at the beginning, if you set your pi k to be not that extreme, like say 1 over k at the beginning, or some kind of uniform distribution of samples from a Dirichlet distribution, it won't be that extreme. As long as it won't be that extreme, your weighted summation of all the data points won't allow you to collapse onto one single data point, right? And similarly, your covariance matrix won't shrink onto 0. That's from a computational perspective. You can see that you keep doing this EM algorithm, it can help you avoid those bad local minimums where you just collapse onto a single data point. Any question? Okay, great. So here we use a concrete example to showcase how typically EM algorithm is run. Like, so suppose we got these data points, right? These data points are green dots, right? And at the beginning, we set the pi first we choose k equals to 2, right? So we might set pi just be half and half. This is my two cluster means, right? Two cluster covariance, which might be just identity or something multiplying with identity because they're just circles, right? So and then in the E step, right? In the E step of the first iteration, you can see that because the equal distribution over pi, right, half and half, right? We'll compute the posterior distribution of the membership, right? All the points which are closer to this blue circle center, they're more likely to be cluster 1, right? All the points closer to the red circle center, they're more likely to be cluster 2, and in the middle, they're kind of like in the middle, right? And then with the with the current posterior, we plug into our evidence lower bound, right? We fix the posterior distribution of cluster membership, just maximize the cluster center and pi vector and also cluster covariance. So this is where we got update of those cluster positions. So you can see that the mean and the means of these two clusters they change significantly, right? It's kind of like appealed by the data points from your current posterior assigned, right? So this is where this blue cluster is here, and this is where the green cluster is here. So finish the iteration 1, and then you do iteration 2. That means according to the current posterior mean, and the covariance, you re-update the cluster membership of every data points, right? According to which you're going to maximize your model evidence again. You can see that your cluster mean and covariance it got updated, right? So just keep doing that. You see that eventually your cluster means are getting more and more separated, right? And also the cluster covariance kind of cover the data points which belongs to the corresponding cluster. And after 20 iterations where you almost converges, you can see two reasonable clusters and cluster covariances. Okay. So YAM algorithm is very fundamental, very popular algorithm. So well, we'll leave some exercise for you. So this two might be in the next homework, right? So we encourage you to derive the YAM algorithm updates for the mixture of a Bernoulli distribution. So remember, for the mixture of Gaussian distribution, we're assuming that data points are sampled from Gaussian likelihood, right? But what if your data point are just the 0 and 1s? Right? Then your likelihood is just Bernoulli likelihood. Can you also do some clustering over that? So then you can adjust your YAM update for the Bernoulli distributions. And the second practice example is to derive the YAM algorithm for Bayesian linear regression. So remember, we're doing Bayesian linear regression. We're assuming that, okay, I have my prior over the weight vector. It might be mu0 and sigma 0, right? And then for every observed data point xn, right? We'll assume that yn given xn w is a Gaussian likelihood from a linear mean is a linear transformation of xn a feature vector, and with some variance. Let me just use v. Right? Then you can write down the joint likelihood to be w and y, right, given x is just the r of the weight The likelihood, we assume the data points are ID, so we got this Gaussian likelihood over all the data points. Condition on W, right? And here, the model parameters includes the prior mean and prior covariance. Okay. And also the likelihood variance. Right. And the latent random variable is W, right? So we also want to know that what is the posterior distribution of W given the data, right? Given data. Right. And how do we jointly estimate this? We can use the YAM algorithm, right? In the each step, given the current theta, right, you compute the posterior distribution of W, right? So this is fairly easy because this is Gaussian multiplied with Gaussian. You do the normalization. It is just another Gaussian. Then in M step, you plug in this QW into the lower bound, right? Then you maximize this lower bound with respect to theta. Does it make sense? Any question? Okay, great. We use one specific model, Gaussian mixture model, and also the YAM algorithm to motivate our variational inference framework. You see that from more general point of view, YAM algorithm is just the instance of variational inference algorithm. So to introduce the variational inference framework, right? Again, this is retreat to the general model, right? Not specific to Gaussian mixture model or linear regression model. So we'll again look at this general model where you have some parameter theta. You parameterize some prior to generate the latent random variable Z. And then given Z, you sample observe data X, right? So if you look at observations, right, you have to marginalize out Z according to the joint distribution, right? So let us, for convenience, let us put aside estimation of theta. Right? So let us assume theta is there, theta is fixed, right? We focus on estimating the posterior of Z given X first. This is our major goal. Right? You will see that if you want to join the estimate theta and this posterior distribution, it can still convenient being done together, there's an inference framework. Right now, let us just assume theta is known. Okay. So if you look at how to compute the posterior distribution of Z given the X, right, this is actually the major challenge in Bayesian inference. Right? So from our discussion a moment ago, we simply assume this guy can be computed in a closed form, right, in the Gaussian mixture model, in the Bayesian linear regression model. It indeed has a closed form, but in most cases, in most practical cases, it is not feasible to compute. The reason is that if you apply Bayes' rule, you have to compute the marginal distribution of the data, right? Okay. In this marginalization, you have the marginalized out Z in the joint distribution. This integration, however, usually is infeasible. So for example, if your prior is a Gaussian, if your likelihood is a Bernoulli likelihood with a sigmoid function, right? Then if you want to compute the marginal distribution, this integration does not have any closed form. You can see that even in a simple scalar case, it's always the case that you're able to compute the posterior distribution. So you can see that. actually the Gaussian mixture model, or any other examples, or the other models that you can directly apply the YAM algorithm is too simple. Because in each step, where it demands that we compute this posterior distribution, in most practical cases, it is not feasible. Then how can we address this problem? Like, how can we address this problem? The idea is as follows. So now that I don't really know how to compute the exact posterior distribution, and in most cases, I even do not know what's the form of exact posterior distribution. It could be a mixture of Gaussian, it could be a student T, it could be any form which I don't know. I do not know. Okay. Then I want to approximate this posterior distribution with some simple form. For example, I just approximate this posterior with some Gaussian distribution. Of course, this Gaussian distribution won't be exact, but having it in my hand is better than we have nothing. Right? So then the question becomes, right? The Gaussian distribution is a large family, right? You have infinite choices of mean and covariance, right? Which particular mean and covariance you believe can best approximate the true posterior distribution? That's the problem we need to answer, right? So it's like, okay, this is my true posterior distribution, right? I don't know how to compute that. Right? I don't know how to get closer to that. Right? My strategy is that, okay, I'm gonna use a simple form of distribution, right, to approximate the true posterior. Right? And there are many candidates in this simple form distribution, right? So then my task is that I want to find out one member in my approximation family that is closest to the true posterior. So this is the idea of the Lorentzian inverse. I'm gonna use a simple form of simple family of distribution to approximate the true posterior. Right? Then my task is just to search the best possible approximation to the true posterior. So here I want to read out this paragraph again, right, to strengthen the idea, right? So now that the true posterior is complicated and tricky to compute, right? Can we find a simple form of distribution, for example, Gaussian, that approximates the true posterior? In other words, can we designate a family of simple distributions from which we find the best member that is closest to the true posterior? Take the example we discussed again, right? So suppose my prior of Z is a Gaussian, and given Z, I got my Bernoulli likelihood to sample the binary variable X, right? And the parameter of Bernoulli likelihood is a logistic function of Z. So if you want to compute the posterior distribution of Z, given your observation X, it is infeasible. I don't know what's the form of the exact posterior. So then my goal is that I want to pick up a Gaussian, right, to approximate this true posterior. The remaining question amounts to how to determine the best mu and sigma squared. So then that leads to a question, right? So what do you mean by best approximation? How do you measure the goodness of an approximation to the branches? Any thought? Any idea that you can come out metric which can measure whether your approximation is good or not? Actually, I haven't discussed such kind of measure, but it's called KL divergence. We mentioned that KL divergence is a way to measure the difference between two distributions, right? And only when these two distributions completely overlap, the KL divergence will be zero. Otherwise, the KL divergence will always be non-negative, right? And the closer the two distributions, the smaller KL divergence. So here, we're going to use KL divergence. Right? Suppose we designate a family of approximate distribution, like to approximate posterior. Right? We if you want to find out which particular member of this family best approximates the true posterior, this can be turned into an optimization problem. Right? I want to minimize the KL divergence between your approximation and the true posterior. Right? And suppose this approximation is parameterized by alpha. That means I just minimize this KL divergence with respect to alpha. I find out the best alpha that can make this KL divergence to be the smallest. That I believe this the corresponding approximation will be the best. Right? In other words, suppose this is true, right? Your KL divergence, your optimization, your minimization of KL divergence is like you're searching over this approximation space, and eventually you find out the best one, which is closest to the ground truth. Does it make sense? But here you can see that cross I put here. Right? So here conceptually it is reasonable, but in practice it doesn't make any sense, right? Because if you want to compute KL divergence, you need to know the posterior distribution, right? Exact posterior distribution. But if you know the exact posterior distribution, why would you like to choose any approximation? Right? It's like chicken and egg problem, right? Because I don't know the exact posterior distribution, that's why I'm seeking for approximation. But if you want to measure the closeness between my approximation and true posterior, I need to first know what is exact posterior distribution. That doesn't make any sense in practice. So of course, in practice, we won't really be able to directly minimize this KL divergence. So we want a procedure to implicitly minimize this KL divergence without the access to the true posterior. How can we do that? We go back to the decomposition of the model evidence, which is derived by applying the Jensen's equality. If we look at the model evidence, so here we will meet any hyperparameters. Assume there are none. So if we look at model evidence, right? If we introduce any third distribution Q of Z by applying the Jensen's equality, we can decompose this model evidence by a lower bound, model evidence lower bound, plus a KL divergence between Q of Z and the ground truth posterior, or exact posterior, right? So our key observation is that the model evidence is fixed. Right? Model evidence is constant, right? So it can be written as the lower bound plus the KL divergence. So that means if you increase the lower bound, you decrease the KL divergence, right? If you can maximize your lower bound, it is going to minimizing the KL divergence. So now we get the idea, right? We can now directly compute this KL divergence. Then we just maximize the lower bound. We maximize the lower bound with respect to this approximation distribution Q. We know that when it's maximized, when it's a lower bound, which is maximum, the KL divergence goes to a D minimum. Then we're done. That's the idea of a variation inverse. So if you look at the computation of variation inverse, what's the computation of this lower bound? We can see that you don't really need to compute any posterior. What you need to do is just to compute the joint distribution, right? And joint distribution is always, you're always able to compute that, right? So that means the lower bound is always much easier to compute, right? So now, I want to emphasize again the key idea of the variational inference. We maximize the variational lower bound, which implicitly and equivalently minimize the KL divergence. So for whichever approximation family you want to use, right? Just use that approximation family to parameterize your Q, right? For example, if you use Gaussian, it might be just Z, mu, and sigma, right? And then you just plug it into your lower bound. You maximize the lower bound with respect to your mu and sigma. You maximize it, and you find the optimal approximation of the posterior. Any questions so far? So here's the global variational inference framework. Like, given a family S of the approximate posterior Q of Z, right? If you want to find out the best approximate posterior Q of Z, you maximize the lower bound, the model evidence lower bound with respect to Q in this family, right? Which essentially is to maximize this guy, right? It's an integration of QZ times this log fractional between the joint distribution and Q of Z. And if you can write it in a more concise way, it's just the expectation under Q over this log fractional. Then that's it. And from this approximate inference framework, right? There's usually a trade-off. So we know that this is just to fulfill the idea that, okay, suppose this is your ground truth, right? This is your approximation family, right? And it's often the case that you want to find out the best family member that is closest to the ground truth, right? So, sorry. The trade-off is that it's often the case, the smaller family you choose, the easier this optimization problem is to solve. And the larger the family you choose, like for example, you can increase the family, right? You can increase the family. So you can expect that by enlarging the family, the optimal approximation will get him closer and closer, right, to the ground truth. But there's no free lunch on that. The whole optimization procedure that maximizes the variational lower bound will get harder and harder. This is a common trade-off in the variational inference framework. And of course, you need to trade off between the computational efficiency, the computational resource, and the approximation accuracy you want. Any question? Okay, great. So let's stop here today. Right? Thursday, we're going to continue discussion of variational inference. We'll talk about several commonly used approximation family, like mean field approximation. And we'll talk about local variational inference, where you can construct some evidence lower bound by using the convex conjugate. You will see why at the beginning we introduced this convex conjugate. It's actually really useful. Okay, see you on Thursday.